Hi everybody, I am Pascal Urien from Telecom Paris, France, and the subject of my talk is innovative dynamic SRAM PUF authentication for trusted Internet of Things. This paper presents innovative dynamic SRAM physical and clonable function authentication for microcontrollers units and bending static RAM. We introduce low-cost PUF extractors designed to monitor MCU power-up and to read SRAM contents. Some SRAM cells, referred as flipping bits, have a fixed content dependent on the voltage rising time. Experiments using double ramp power-up waveform show that this cell switch at low voltage value below 500 millivolts. Because the digital part of the MCU is not working when flipping bits switch, we propose a simple SRAM dynamic authentication protocol based on slope and square power-up waveform, whose goal is to detect clone MCU. A SRAM memory cell is designed with 6 CMOS transistors and includes 2 inverters, I1 and I2, connected in series, that's to say head to tail. If these logical inverters have not identical electrical charge characteristic, the memory cell will switch to a fixed value upon power up. This effect enables to extract a set of bits from SRAM memory after powering up. Typically, PUF bits are used to forge secret key associated to symmetric or asymmetric cryptographic algorithm. Given Fi, the transfer function Vout equal F of Vin of an inverter I, the stationary state implies that F1x is equal to F2 minus 1x. If the two inverters are similar, then Fx is equal to F minus 1x. This is what defines free solutions. When the SRAM cell is switched, the output voltage is either V low, logical 0, or V height, logical 1. Due to NMOS and PMOS symmetry, VDD/2, that's to say half of inverter feed-in voltage, is always a possible solution. During powering up, SRAM output voltage follows VDD/2 until the inverter gain is enough for switching towards V low or V height. For fully skewed cells, that's to say highly mismatched SRAM, the cell always takes a fixed value. The voltage Vs at which the transition occurs is dependent on the cell. Previous papers demonstrate voltage ramps effects on partially skewed cell RAMs. Given a ramp with slope VDD/T, flipping bits are observed for slope alt values. Flipping bits are created by capacitance dissymmetries, while most of PUF bits are due to voltage threshold VTH differences. In other words, voltage runs reproducibly switch the value of some SRAM cells at power up. We design a low-cost PUF extractors. The device under test is running a SRAM probe software, which communicates thanks to a serial link. It is powered up by a digital to analog converter with a 4096 bits resolution, whose output is optionally associated to an amplifier. The PUF extractors control the power-up waveforms about 4 outputs per millisecond and reads the SRAM content of the tested MCU. We previously published experiment for ATMEGS 8 processor. We log for each SRAM cell key the number of one occurrence for n power ups, using a slope t, noted SNT key. Some cells are always seen at 1, that's to say SNT key is equal to n, or 0, that's to say SNT key is equal to 0, and define the PUF domain. The remaining cells are referred as noisy, that's to say SNT key is greater than 0 and less than n. For example, with n equal to 250, we get a set of measures SNT key for slope VDD/T with T expressed in milliseconds. The comparison of a measure SNT with a reference SNREF-TREF is a set of tuples SNT key, SNREF-TREF key. The common PUF domain is a set of tuples either equal to NNREF or 00. Flipping bits are the set of tuples N0 or 0NREF. Noisy cells comprise the tuples noisy, noisy 0, noisy NREF, 0 noisy, and N noisy. For low rising time, there are no flipping bits. Here are some experimental results for ATMEGS 8 MCU. For fast rising time, there are about 360 flipping bits. This number is divided by 2 for t equal 100 milliseconds and reaches 0 for t less than 512 milliseconds. The figure on the right shows a graphical representation of flipping bits, colored in red, for S250-64, that's to say 64 millisecond slop, versus S250 1024, that's to say 1024 millisecond slop. The PUF common domain is colored in greens, always 1, and yellows, always 0. Noisy cells are colored in white. Let's introduce double slops SU waveform. A voltage ramps modify flipping bits SRAM cells whose content is B0 key, either 1 or 0 for a slop S0, and B1 key equal to 1 minus B0 key for a slop S1. We build a voltage waveform SU that mixes two slope. For voltage values ranging from 0 to U, we use slope S1, and for voltage values ranging from U to 1, 1 meaning VDD equal to 5 volts, we use slopes S0. At the end of such power up, we observe a cell content, BU key. Obviously, for U equal to 0, that's to say slope S0, we find B0 key. And for U equal 1, that's to say slope S1, we find B1 key, that's to say 1 minus B0 key. We want to find the U switching value Vs for which a key SRAM cell's content switches from S0 output to S1 output, and to observe the threshold distribution Vs key. In order to reach these goals, we perform 250 times 25 measures with S0 equal S64, that's to say 64 millisecond slop, and S1 equals to S1024, that's to say 1024 millisecond slop. For U values starting from 1 bit resolution, that's to say U equal 1/4096 to 250 bits resolution with an increment step of 1 bit resolution about 1.2 millivolts. We store the number of one occurrence ranging from 0 to 25 in B key U records. The figures on the right show B key U curves for two flipping bits. Obviously, the region around the thresholds is noisy. A small U interval is observed to decrease B key U from 25 to 0. The two threshold points Vs are about 2.45 and 4.30%. The figures on the right present the switching voltage distribution. The S0 PUF domain is on the left, green for 1 value and yellow for 0 value. The S1 domain is on the right and is colored in red. The frontier between the two domains is noisy and is colored in white. Roughly speaking, these domains are separated by a line for U ranging from Vs min to Vs max. Let's now introduce slope and square RX waveform. We observed that flipping bits are created at low voltage Vs. we define RX waveforms, which comprise two parts: a slope S6 from 0 to Vx equals 625 millivolts, and then a fast rise from Vx to VDD. For fast rising time, RX waveform should create flipping bits. For low rising time, RX waveform should not create flipping bits. Therefore, we suggest to use RX waveforms such as R64 and R1024 in a random ways in order to create SRAM PUF with and without flipping bits. Because processors are not working at low voltage, malicious software cannot guess the induced memory fingerprints. Finally, we propose a simple dynamic SRAM PUF authentication protocol. Look at SRAM contents for two RX power-up waveforms, I64 and R1024. The I64 SRAM content has about 200 flipping bits. These contents are determined at low voltage, 512 millivolts, before Lux and VADORs have a digital life. VADORs and Leah know these SRAM contents. In order to authenticate Lux, Leah uses power-up waveforms, either R64 or R1024 in a random order. Lux will always produce the right response, while VADOR will make a random choice. So after n tries, the probability of 0 error for VADORs will be 1/2 power n. Thank you for your attention.